Welcome to the second video. In this video, we are going to talk about some fluid properties. As an introduction, I would like to show you a short video in which you're going to see some quite complex fluid behavior. This video, which shows a simulation of a tsunami hitting a city, illustrates quite nicely how complex fluid behavior can be. If we now want to model such a fluid system or want to describe it, we have to discuss some properties of the fluid to be able to model its motion and all the physical effects that takes place during such a complex event. In principle, you can say that fluid behavior is governed by fluid properties. There exist various fluid properties, which we will not all cover in this lecture. But in this video, I would like to discuss some of these fluid properties, which we need in the following course. Let's start with the density. As you can see from the image on the right-hand side, density, of course, plays a crucial role when you want to describe the motion of fluid. A second very important fluid property is the viscosity, which describes the ability to flow. In the video, you just saw a wave of water hitting the city. You can easily imagine that a wave, for example, made out of honey would look quite differently. And this is mostly due to the differences in viscosity. We will discuss viscosity in more detail in a couple of minutes. Another fluid property we are going to talk about is the compressibility. As you already learned in the first video, the main difference between liquids and gases is the incompressibility of liquids. To be able to describe surface effects, for example, free surfaces or the gas-liquid interfaces, you also need to consider fluid properties. This will be done in detail in another lecture. Today, we will only discuss some very basic fluid properties that are relevant for surface effects. In principle, any property of a fluid is dependent on the state variables, which we discussed in the first video. The change of a fluid property as a function of these state variables is described by a material law. In some cases, the properties are only weakly dependent on the state variables and can thus be considered constant. Let's start with the density. The density is considered to be an intensive property and is defined as mass per unit volume (NSI) units. Beside the mass density, there are some related density properties. The first one is a particle density. The second one is a concentration, which is usually given in mole per liter. And the last one you might already know from chemistry is the pH value. The next fluid property we are quickly going to discuss is the viscosity. Dynamic viscosity, which is here denoted by eta, is defined as a proportionality factor between shear rate and the shear stress. And this is in the units of Pascal times second. And viscosity more or less describes the ability to flow of a fluid. That means the lower the viscosity is, the less energy is dissipated due to friction. And closely related to the dynamic viscosity is the kinematic viscosity, which is defined as the ratio of the dynamic viscosity and the density. Please be aware that in literature, dynamic viscosity is often written with a mu. In this course, however, dynamic viscosity is always referred to as eta. On the right-hand side, I have prepared a video for you in which you can see how fluids with different viscosities behave. In this video, you can see the filling of 3 different glasses with 3 different liquids. Please notice that the viscosity of water is lower than the viscosity of olive oil, which is again lower than the viscosity of honey. As you can see, the behavior of the 3 liquids is quite different. This can be related to the inner friction, hence the ability to flow of those 3 different liquids. I hope this video gives you an idea how the fluid behavior depends on the viscosity. According to their viscous behavior, we can classify fluids. The most important class of fluids we are mostly dealing with in this course are liquids with a constant dynamic viscosity. These liquids or fluids are called Newtonian liquids. In general, however, the viscosity is shear rate dependent. As you can see on the left-hand side, for a Newtonian fluid, the rate between the shear stress and the shear rate is constant, leading to a linear graph in this diagram. Another case would be a Bingham fluid. Here, the shear stress is not zero when the shear rate is. A common example for a Bingham fluid is toothpaste. Beside those two different classes of fluids, there are also the pseudoplastic and the dilatant types of fluid. On the right-hand side, you can see a table in which the viscosity of different fluids is written down. As you can see, liquids tend to have a higher viscosity than gases. Just like we saw in the video on the previous slide, the viscosity of water is lower than the viscosity of olive oil, which is again lower than the viscosity of honey. This means that when honey flows, there is more friction, so more energy is dissipated. On the first slide, we discussed that most fluid properties depend on the state variables. While this might not be the case, for example, the density of liquids, it is definitely the case for the viscosity of gases and liquids. On this slide, I would quickly like to discuss how the temperature influences the viscosity of gases and liquids. The behavior is qualitatively plotted on the right-hand side. As you can see, for gases, the viscosity increases with increasing temperature. This can be explained that with higher temperature, there are more collisions between the individual molecules that make up the gas. This leads to a larger viscosity. The temperature dependence of the viscosity of gases can be modeled with this expression. On the other hand, the viscosity of liquids decreases with increasing temperature. This can be explained with a higher mobility of the molecules that can now more easily overcome the cohesive forces. And this leads to a lower viscosity. And the viscosity of liquids can be modeled using the Arrhenius model, which is given here. And these two expressions, here and here, would be the material laws for the viscosity. The third fluid property I would like to discuss is the compressibility. The compressibility of a fluid is defined as a relative change of a volume by a pressure in units of 1 per Pascal. We already discussed that liquids are nearly incompressible, while gases are. This is illustrated on the right-hand side. So for liquids, we can always assume that the compressibility is 0, or that they are incompressible, meaning that their density does not change. But for gases, we have to account for the compressibility. If you look at the right-hand side in the lower picture, you can easily see that the density for this system is lower than the density in this system. So gases are compressible. And for the isothermal compressibility for an ideal gas, you can model this change of state by the law of Boyle-Mariotte. We will discuss the state changes of gases and calculate some examples in the lecture. In systems where you do not only have a liquid, but also a gas, you always have a phase boundary, which is the boundary between those two states. In such a system, you have to consider additional effects. One of these effects is the evaporation. And this means that all liquids have a tendency to evaporate into the gaseous phase, and that all gases have a tendency to condense back into the liquid phase. We already discussed this phase transition in the first video. This phenomenon of evaporation leads us to the fluid property of the vapor pressure. And to understand the vapor pressure, you can consider a closed vessel, which is imaged on the right-hand side. Here, after some time, an equilibrium is reached between evaporation and condensation, meaning that the same amount of molecules that evaporates from the liquid phase to the gaseous phase is condensing back from the gaseous phase to the liquid phase. And in this case, the vapor is saturated. And this means that the pressure inside the vessel is the vapor pressure is equal to the saturated vapor pressure. And this vapor pressure that is now in this vessel is of course temperature dependent. And the boiling point of a liquid is now defined as the temperature at which the saturated vapor pressure is equal to the surrounding atmospheric pressure. With the introduction of the boiling temperature, we have to discuss the difference between boiling and evaporation. Let's start with evaporation. Evaporation is a surface phenomenon, meaning that the vapor pressure in the case of evaporation is lower than the atmospheric pressure. In such a system, bubble formation is not possible within the bulk liquid because the bubbles would, of course, instantly collapse. In contrast to that, boiling is a volume phenomenon. Here, as imaged on the right-hand side, the vapor pressure is higher than the atmospheric pressure, and this means that all the bubbles that are formed within the bulk liquid can stay there and do not collapse. So boiling is a volume phenomenon. And during the process of boiling, the temperature of the liquid cannot rise above the boiling temperature. Now that we have understood the basic concepts of evaporation, vapor pressure, and boiling, we can discuss how we can model the fluid property vapor pressure. As you can see on the right-hand side, the vapor pressure, in this case for water, has an exponential dependence on the temperature. And if you have a gas in equilibrium with its liquid phase, you can use the Antoine equation to model this. The Antoine equation is given here. Please be aware that A, B, and C are constants, meaning they depend on the liquid, and that these constants change above the boiling point. So if you use the Antoine equation, always check that you have the correct set of parameters. You can find those for various liquids and temperature ranges in the literature. Please also note that the result you get from the Antoine equation is not in Pascal or any other SI unit, but in millimeter of mercury. This is an historic unit which can be easily converted to SI units. When you have more than one gas, for example, a mixture of gases, each gas contributes a partial pressure to the total vapor pressure.